All right, today we're going to rethink gravity. And I mean really rethink it. We're going to start with something super simple, an apple falling from a tree, and we're going to follow that single idea all the way to some of the biggest, most mind-bending questions we can possibly ask about our universe. So let's just dive right in by challenging something we all think we know. When you see an apple fall from a tree, what's actually happening? It seems like the most obvious thing in the world, right? For centuries, we all just went with Newton's idea. Some mysterious force called gravity reaches up and pulls the apple down. Simple. But then Einstein came along and completely shredded that script. He said, no, you've got it all backward. From the apple's perspective, it isn't falling at all. It's just floating there, weightless. The real movement is the entire Earth accelerating upwards to smash into it. The feeling of the ground under your feet right now, that's the Earth pushing up on you. And this gets us to this really core idea called inertial motion. In Einstein's universe, that apple in freefall is in its most natural state. If you could tape a little motion detector and accelerometer to it while it's falling, you know what it would read? Zero. Nada. It feels no force, no acceleration. It's just chilling. Meanwhile, an accelerometer in your pocket would be reading a constant upward acceleration of 1g. We're the ones who are accelerating. We're the ones fighting our natural path through the universe. Okay, fine. The Earth is always pushing up. I can kind of see how that explains a falling apple. But what about orbits? If gravity isn't some force pulling things together, why on earth does the Earth circle the sun? What stops us from just flying off in a straight line into deep space? Right? This is the central puzzle. If there's no invisible rope tethering the Earth to the sun, what is holding our solar system together? Well, the answer isn't a force at all. It's geometry. There's a brilliant analogy that makes this click. Imagine two cars, okay? They're on the Earth's equator, about 1,000 kilometers apart. Both drivers lock their steering wheels dead straight and start driving due north at the exact same speed. Now, even though neither car ever turns, what's going to happen? Their paths will get closer and closer until they eventually meet at the North Pole. And that is the whole mind-bending takeaway. If you were looking down from space and thought the Earth was flat, you'd swear there was some weird magnetic force pulling those cars together. But there's no force. They were just driving in what for them was a straight line on a curved surface. They were just following the lines of longitude. And that right there is the engine of general relativity. It's this beautiful two-way street. A massive object like our sun doesn't pull on the Earth. It creates a huge curve, a deep well in the very fabric of space and time around it. And planets like Earth aren't being pulled, they're just following the straightest possible path they can through that curved space. An orbit, really, is just what moving in a straight line looks like in a universe that is fundamentally curved. So now, let's take this idea of curved spacetime and see what happens when you push it to its absolute limits, because that's where we find some of the most bizarre and truly fascinating stuff in the entire universe. You know, one of the wildest predictions of general relativity is that gravity doesn't just warp space, it actually warps time itself. It's called gravitational time dilation, and what it means is that time literally passes more slowly the closer you are to a massive object. It's a real, measurable effect. It means that right now, your head is aging just an infinitesimal bit faster than your feet. Wild, right? And this time warping is actually the key to solving that famous old puzzle, the twin paradox. You know the one, a twin flies off in a rocket near the speed of light, comes back, and is now younger than the twin who stayed on Earth. How is that possible? Well, on the trip out and the trip back, the space twin sees the Earth twin's clock running slow. But here's the kicker. That moment they have to slam on the brakes and accelerate to turn around and come home, in that brief moment, from their point of view, they see the clock on Earth leap forward at an insane speed. That moment of acceleration is what seals the deal and makes the Earthbound twin the older one when they reunite. Now, the ultimate expression of this warped spacetime has to be a black hole. This is where the curve is so extreme that at a certain point, the event horizon, the path to get out literally curves back in on itself. Not even light is fast enough to escape. And for a distant observer, like us, watching something fall in, well, because of that infinite time dilation, it would look like it just freezes at the edge, stuck there for all eternity. But here's the thing. For all of its power and its pure mathematical beauty, Einstein's theory of a smooth, curved spacetime, it hits a wall. It breaks down when we try to look at the universe at the absolute tiniest scales. And this brings us right to the edge of known physics. So here's the fundamental conflict. General relativity is smooth. It treats spacetime like a perfect, continuous rubber sheet. But quantum mechanics, our rulebook for the subatomic world, tells us that everything, energy, matter, you name it, comes in these little discrete packets or chunks. It's a pixelated world, and you just can't reconcile a perfectly smooth, continuous sheet with a chunky, pixelated reality. The math just falls apart. Right now, there are two main contenders trying to solve this problem, and they're very different. On one side, you've got string theory. It says that deep down, everything is made of these tiny, vibrating strings. But for the math to work out, it needs a bunch of extra hidden dimensions. For string theory, space-time is the background. It's the stage where the strings perform. But then you have loop quantum gravity. It says, no, space-time is the performance. It's not a smooth background at all. It's actually built from a network of these tiny, indivisible quantum chunks, and it works just fine in the 4 dimensions we know and love. And now, for our final puzzle, we have to zoom all the way out, from the impossibly small to the scale of the entire cosmos. And here we're left with a truly profound question. Why are the fundamental laws of our universe so perfectly, so exquisitely calibrated for life to exist? Let's just look at one number, the cosmological constant. It's a value that basically controls the expansion of the universe. And its value is fine-tuned to a precision of 1 part in 10 to the 120th power. I mean, that's a 1 with 120 zeros after it. It's a number so huge it's meaningless. If that value were just a tiny, tiny fraction different, either the universe would have expanded so fast that stars never formed, or it would have collapsed back in on itself a split second after the Big Bang. No stars, no planets, no us. To try and get a handle on those odds, here's an analogy. Imagine throwing a single dart from one edge of the observable universe all the way to the other side, and hitting a target the size of one single atom. That's the kind of ridiculous precision we're talking about here. Now, one response to this is something called the anthropic principle. It basically says, well, of course we find ourselves in a universe with life-permitting laws. If the laws were different, we wouldn't be here to notice. But that doesn't really answer the why, does it? It's kind of like a prisoner surviving a 100-person firing squad and saying, well, of course they all missed, otherwise I wouldn't be here to think about it. It's true, but it doesn't explain why they all missed. This leaves us staring at 2 massive and profoundly different explanations. Possibility 1, the multiverse. It's an infinite cosmic lottery. There are countless other universes, each with its own random set of physical laws. And by sheer dumb luck, we just happen to live in the one where the numbers came up right for life. The other possibility, the game was rigged, that the constants of nature were intentionally set to these precise values for a reason. And so, that's where a simple falling apple has led us. From the ground rushing up, to the curved fabric of space-time, to the quantum frontier, and finally, right here, to the ultimate question. Is the universe we know a fantastically lucky accident in an infinite cosmic lottery? Or is it something more? The answer? Well, it's still out there, waiting to be discovered.